Welcome everyone to this second meetup of the Modern C++ Meetup group, and here we go. Have fun.
Well, I hope so. Depends on what excites you and what is fun for you. My name is Mats Brorsson. So I have a bit strange background in software development. I have a long history in academia before moving here down to Luxembourg, and so I spent my most of this century actually in Stockholm at KTH, University of Technology, and where I was working on various aspects of parallel computing, in particular hardware support for it, but also runtime system support, so that the developers would do as little work as possible, making good progress. Since then, last 2 years I've been working with a company called Olamobile. There is a colleague of mine here doing C++ development for real-time bidding, so on ad tech business. So trying to as quickly as possible find the most profitable match between user and advertiser as possible. The real story is a little bit more complicated than that, but that's something we can talk about over the beer. Since a few days, I started to work with a company called Satalia, which is an optimization company based in London. I work remotely from here. This is a company who are dealing with all kinds of problems that require sort of sophisticated solutions in terms of optimization problems like logistics, how to find the best routes from A to B, and with various constraints. If you have drivers available at certain times, and you have loading docks available at certain times, and things like that. Not only logistics, but that's an example that's we're using. Today I'm going to talk about some options and trade-offs for parallelism and concurrency in modern C++. Maybe I'm promising too much, because I will not talk so much about plain concurrency, but pure parallelism mostly. So here is an outline of what I will be talking about, and I probably have a lot more slides than you will bear. So I would probably stop when is the time, Brandon?
We have 1 hour.
Yeah, so I would probably try to stop about 8:15, and then you can ask questions if you like, and so on. So, but otherwise, I've prepared things for introduction to why we are actually needing to do this in C++. What C++ can give us standardized since the C++ 11 standard, and then look at some higher abstraction models, in particular OpenMP, which is the one I have been working mostly with. But there are other ones which are particularly useful for C++, namely TBB, threading building blocks, and the parallel standard template library, which is a new feature of C++ 17. And we'll come to the other stuff when we get there. Since over a decade now, parallelism is everywhere in computer system. In any computer systems, you have many levels of parallelism also. You have server-level parallelism, multiple servers that you need to work together, and you need to synchronize them and so on. This is sort of what most people see and work with. This is a distributed memory system, and rules and the way of developing software for that is typically has its own regime, and I will not really go deeper into that. There are two sort of flavors of that. You have the ones which is used for high-performance computing, where you have frameworks like MPI, Message Passing Library, where you have all the nodes working together on the same problem, and you have then on the other side, which is more common, you have the distributed computing problems when you have more loosely coupled problems. What I will focus on here is the support in C++ for multi-core architectures where you have shared memory. But there are more levels of parallelism. You have instruction level parallelism, which you typically do not need to deal with yourself. That's the compiler issue, to schedule instructions so that they execute the best for the particular architecture that you're running on. So if you really want to cram out the most performance as possible on your system, make sure that you compile with the architecture flag that's set for the architecture that you're running on. Vector parallelism. That's more recent, and I have a special slide on that. Every processor now has pretty wide vector units. So I think the latest Intel processors have this AVX 256. So you have 256 bits wide vector registers where you can do typically like 16 floating point operations in one go. Normally you do not want to deal with that yourself because that's pretty complicated. Luckily, compilers are pretty good at dealing with this. And then thread parallelism, that's the normal parallelism that you get from having multiple cores inside a machine. To complicate things, Intel and others, in particular Intel, they also like to have a distinction between hardware threads and software threads. So you have several cores, like this laptop here has 2 cores, but each core has 2 hardware threads. So from an operating system point of view, it looks like it has 4 cores, but only 2 can actually execute in parallel, really in parallel. The other sort of hardware threads can boost performance. They are there to utilize the hardware better, but doesn't really provide true multi-threading. Okay, so vector versus thread parallelism. So vector parallelism maps naturally to sort of natural regular data parallelism, when you have data that you will want to operate the same thing on over and over again. And the way to vectorize is, hopefully you can do it automatically, and I will actually show you an example of how that is done. Or you use the vector intrinsics that are available in the compiler. You really don't want to do that, because that's, unless you have some specific needs. Then you have some compiler hints. So Silk Plus is an extension to GCC. It's a spin-off of an MIT research project. It was for a while a compiler of its own called Silk++. Then Intel acquired that company and baked it into the Intel compiler, and then it made it open source. So it resides now in GCC and in Clang. And you just have to write -f Silk Plus to get it running. Supposedly, I haven't actually worked with GCC version myself. But anyway, Silk Plus has an array notation that helps to tell the compiler that this is code that is data parallel, generate vector instructions for it. And OpenMP has a SIMD pragma. OpenMP works with pragmas that are pragma OMP, and the SIMD pragma in front of a for loop tells that this for loop is a data parallel for loop and can be parallelized. In many cases, actually, you don't need to do this. So I will show you an example. I will show you a really cool website. Oh, by the way, that was the Silk Plus website, so silkplus.org. If you're interested in that, that's a cool thing. How many here have heard of Godbolt? That's a really cool website. You type your C++ code to the left, or C, and then you get it immediately disassembled to the right, and you can choose of many compilers, not only GCC but different versions of GCC, Clang, MIPS, ARM compilers, and whatnot. But I wanted to go for GCC, and I'm going to pick one of the later ones. I'm going to remove the OpenMP stuff. Okay, so here you can see it with no optimization, tons of code. This is a Saxby loop. I will come back to that in the presentation. The meat of it is this purple stuff in the beginning. So it's a loop running a number of iterations, and here you can see it's a scalar. Well, if you know x86 assembly, you can see it's a scalar code. Now, if I turn on optimization, this purple thing is reduced to these 5 instructions here, the yellow now, and you see it uses the SS, which are the AVX instruction set, and you see the compiler automatically noticed that this is a vectorizable loop and generated this code for it when it optimizes. So this is a good tip. Godbolt.org. It's a name. The Matt Godbolt is the guy who maintains this and runs it out of his own pocket, and his name has become both a noun and a verb. I want to Godbolt this on Godbolt. Okay, some key features to keep in mind when you want to parallelize stuff in any case. The picture here shows one of the tools that are available if you want to analyze stuff really deep down. It shows for each thread green when you compute and red when you have to stall or wait for something. And of course you want to remove the number of red fields here and have as much green as possible. Think hard about data locality if you want to run fast code. That applies also to sequential code. Make sure that you have chunks of data that fit in the cache. Know your cache size and make sure that you reuse data as much as possible. Try to avoid cache conflicts. One of the most common when you're dealing with parallel computing is maybe fault sharing. You may know that caches are divided into chunks that are cache lines, and each cache line contains a number of data elements. And if 2 threads are updating 2 data elements that reside in the same cache line, there will be a lot of communication back and forth in the hardware, even though the software itself does not communicate. That's fault sharing. So data locality is important. Parallel slack means that you should try to expose in your code much more parallelism than the hardware has. So if you have a 4-core processor that you run on, you should strive for having parallelism that is a factor of 40 at least, or 10 times more than. Otherwise, the overhead of managing the parallel activities will be sort of overshadowing the use of it. Try to achieve good load balance, because if the various threads have not equal amount of work to do, some will wait for the others, and that time will be wasted. I could spend several lectures talking about performance sort of in itself, but I'm going to try to go down to code as quickly as possible. Okay, why doesn't this work? Okay, resort. Okay, so as an example to begin with here, I'm going to talk about SAXP, which is a code to scale a vector. So it scales a vector by a factor added by another vector. So I will show the code soon, and this is a single precision floating point algorithm. DAXP is used for double precision. To note here is that this code has very low arithmetic intensity, so it's not really the best in terms of scaling. Arithmetic intensity means that it has little arithmetic work compared to the amount of data consumed and produced. Only 2 floating point operations while you read 8 bytes and write 4 bytes. So keep that in mind when you see the numbers later on. We're going to utilize the map pattern, which is one of the parallel patterns that exist. The map pattern is one of the most common and one of the most useful patterns for parallel computing because it applies a function to every element on a collection of data. So that's useful for both vector parallelism and for thread parallelism. Embarrassingly parallel, it's called. It's usually often combined with other patterns like reduce. So you have map reduce, you have map followed by reduce, and I will come to reduce a bit later on. All of you who responded to my survey said that you had worked on C++11 threads, so this should be clear to anyone that you can declare a thread and pass arguments to it, so I will not spend more time on it. So here is an example of how to implement the SAXP with explicit threading in C++11. So let's see what's going on here. So here is the meat of the SAXP loop. I should have written a serial loop here to show you, but basically this is the loop here. You have x, an input vector, a scaling factor, y, another input vector that you add to it, and then you write it to the y vector here. So the way I parallelized it here with C++ threads is that I have a vector of threads. I create the threads and push them onto this vector. So I have a number of threads. I decided, hard-coded, that I want to create a number of threads. And then I push the function here that carries out the calculation, function name, the arguments to the function, the floating point a here, a reference to x, a reference to y, and threads, number of threads, and y and I, which is the thread identity, sort of local thread identity in this case. Okay, and then when I've done this, the threads go about and do their work. They will calculate the stuff, and then we have to wait for them all to finish in order to be done with it. And each thread calculates a chunk of the total amount of work to do. So basically you have one thread dealing with this slice, one with this, and so on. And the way to do that is basically to calculate based on the size of the input vector. We sort of assume here that x and y are of equal size. And taking the thread ID, which comes from the I here, multiply by the number of elements and divide by number of threads. Then you get the starting point of this particular thread, and then you get the ending point by doing similar calculation. And then you loop from start to end. I claim that this is the analogy to assembly level programming, but with threads, if you want to do parallel computing. The meat of the code is here. That's basically what you care about, but you have to write all of this and all of this to make it parallel, to divide the work to them, and it's not optimal. So substantial amount of extra code over the serial, inflexible scheduling of work, which you can see here. If you happen to have a code which Saxby is very regular, every iteration is the same. But what if every iteration is not the same? They have different amount of work. So this is an example where you have a function instead of this is basically the inner function here that we had before, but we have some kind of map function that do some arbitrary work. Okay, you can do a similar kind of way of similar structure, but instead of having a normal for loop in here, you have a while loop that goes and fetches the next index dynamically. So this means that the first thread goes and executes the map, and the next one takes the next I iteration here, because it atomically, we have an atomic variable here that you increment for every iteration. So even if one iteration takes a really long time, the other threads can go and grab other iterations one after each other. But it suffers from the same problem with the previous one. It's really cumbersome, it's inflexible, a lot of extra code. And the variable updating, the atomic variable, can become a bottleneck. Okay, if it becomes a bottleneck, then you just chunk it. What does that mean? Well, you do a chunk, you fetch a chunk instead of a single element, and then you have an inner loop that works on the chunk, and then when the chunk is finished, you go and fetch another chunk. It's a trade-off, but it more or less works. Going back to performance, just want to say a few words when you have a map, because map is the sort of really the most important parallel pattern here that you should know how to work on. If you find yourself having a sequence of maps, try to combine them so that you have one map that do a sequence of things instead. Less data to load and store, but there are some explicit changes that you may need to do. You may need to make sure that, for instance, one map here doesn't need data that another map up here produces. Then you need to have a synchronization in between them to deal with the data. But otherwise, if you have straight lines here, you use the same kind of data, but just in multiple steps. This is good. You may also want to think about dividing your maps into chunks like this, so that you have so that these slices refer to maybe a processor or a core or a thread or something like that, and let them work together. I want to show you now a little bit code. Okay, so can you see this code reasonably well? So here I have gathered a number of Saxby implementations, and why this doesn't work, I don't know. There's something. Okay. So some keys are not working. I don't know why. In particular, the number key. Okay. Let me come back to that later on then. It's difficult when I can't type. Okay, let's see if we can figure out that later on. Sorry about that.
Don't you have your shift key?
It has changed the
Okay.
This is the first time I'm holding a presentation from this computer, so I'm not sure. Okay. So this is where we are. I'm only here now. Let's look at a few more high-level abstraction models. So this is 3 ones which I recommend that you use instead of the explicit thread. Okay, the OpenMP one is the easiest, in my view. It's a little bit C-like. It doesn't work always that well with new C++ features, but in most cases it works pretty well. So OpenMP has a very easy way of parallelizing for loops that are parallel. You just tag a pragma OMP parallel to make it parallel, and then for to tell the compiler that the next statement is a for loop, and then you have yourself need to ensure that this is there are no side effects. The iterations are really parallel because they can execute in any order, and then the compiler together with the runtime system will divide these iterations that the for loop specifies and execute this code on them. So that's a really, really simple way of doing it. There are many more complicated things that you can do. You can, for instance, specify that you have a schedule which is dynamic, which means basically it goes back to this atomic variable for the iterations. So the compiler will then divide the iterations dynamically one by one, and you can have a chunk to the schedule, so that each iteration, you get a chunk of iterations, and then you work on that. So basically the same thing you saw before with the dynamic stuff, but much more succinctly expressed. The threading building block, TBB, is a pure C++ solution. So OpenMP exists for C, C++, and Fortran. It comes from the high-performance computing world, and that's why it hasn't really caught up with the C++ stuff. TBB, on the other hand, is a pure C++ solution. It's developed mainly by Intel. They have an open source version you can use, or you can buy the product if you like to pay. But they are, well, more or less equal. Obviously, the paid product has some features and performance that the open source doesn't have, but it's not a big difference. So there is a parallel for function in TBB. You specify the indices, or the starting and the end, and then you have a lambda, you pass it a lambda, to do the inner loop. So it's almost as easy as the OpenMP. And equally easy is to use the new parallel standard template library in C++17. The algorithm to use, and if you haven't started to use STL algorithms, do that. Because there are so many things that others have done and debugged and stuff like that you don't have to repeat yourself. So anything that need to work on many things. I mean, sort. Also, sort is done in parallel in the new STL. But transform is the algorithm to use for the Saxby code, and it's very similar to the TBB version. You make first you tell it this is going to be parallel. You can specify sequential also. You tell where the x begins and where x ends, and then where the y begins in the input statement, and where you want to put the output statement, the one you think you return here, and then you make a lambda of this code. Very simple. So I don't have any time to really go into details on any of these models. I will go a little bit more into OpenMP, but I urge you to go and look at TBB and parallel STL. Yeah?
Why not begin twice?
Okay. There's a lock screen.
Oh, well.
So the x here is this one. That's the sort of the main array you're working on. The y here is this y here, and it's assumed that you have the same number of elements in the y as in the x. And this one is an iterator for the element that you return. So that's where you will store the result. So you read it here and you store it in the return. You could have had a third array or vector if you like. So this is sort of a picture of how the OpenMP version of this works. Fragmented Parallel creates the threads. In reality, it will reuse threads in a thread pool. Fragmented OpenMP will divide the work of a for loop among these threads. And if you don't specify anything else, you will get sequences of iterations on each thread. So if you have 16 iterations and 4 threads, they will get 4 iterations numbered like here. And then the code, the for loop ends with an implicit barrier, meaning that the program will not continue until all 4 threads, in this case, have finished their execution. Okay. I want to talk a little bit about OpenMP and how to deal with other patterns, like the reduce pattern. So the reduce pattern is a pattern where you want to combine many elements into one single scalar element. And you have a combiner function denoted by these blue boxes here that combine the values, and it has to, of course, to be associative, otherwise the order is important. So here is an example of how you do that serially. Dot product, you have 2 vectors and you multiply each element and combine them into a sum. So this is actually a map, and the summing here is the reduction. And if you want to do this in parallel, what you can do is you divide each reduction, you do a parallel reduction into a partial reduction, and then you have sequentially a master thread or something like that that combines them to a scalar value. And again, this is if you want to do this in sort of normal threading, it's pretty cumbersome. It's similar code as we've seen before. You have the array of vectors. The new thing here is that we have a sum array, or some vector, that you pass into the function that you create with the thread, and the reference to it, so that you create values here to this sum, and then when all the threads have joined, you sum all the sum arrays up into a global sum. This has terrible performance. Anyone can spot why? Well, the reason is because you have sum array. I have terrible handwriting here, but and you have various elements here which corresponds to the local sums of each thread, and so one thread will write here, another one will write here, another one will write here, and maybe the cache line is about this. So since you constantly update this sum, there will be fault sharing. So each core, so threads sort of are proxies for core. So each thread will execute on the core. So each core will have a local copy of this sum array, or a partial part of sum array in its cache. So every core has its own local private cache. And whenever you store something to that cache line, the processor will go out in hardware and ask other cores, do you have this cache line? If so, throw it away. And if it has it and has it in an updated version, it has to also communicate to this core that it got a new value. So this truly kills performance tremendously. A factor of 100, things like that, if you have a number of cores. So that this is really bad. You may improve it by using the futures and async feature of C++11. So instead of creating threads, you create a number of futures and launch them asynchronously using the async feature. Otherwise, it's pretty similar. In most cases, in most implementations, this will lead to one thread per spawning here. But the difference here is that you don't communicate. You have a local sum that you execute here and return it as a return value, and then you can sum it up later in here. So it has the same structure as before, but it doesn't suffer from the fault sharing as before. Okay. I want to finish with saying a few words about tasks. Task parallel models, which is really my pet topic. I don't know why this keeps coming. Okay. So the main challenge with writing parallel software is that it's difficult to write composable parallel software. So you write with threads, and then you link with some libraries that has threads and so on. You don't really know how they work together. Parallel models of different languages doesn't really work together. It's poor resource management, and it's difficult to write portable parallel software. Things that you write once and then it works well on many different kind of systems. So what I've worked on in academia for a while, and which has become quite a big thing also in the industry, is to make task parallel models of first-class citizen. So basically, you want to expose parallel activities called tasks, not threads. You don't want to you don't want to even see a thread in your system, and you have a runtime scheduler that will map these onto the available hardware. So here's an example of how it might look in OpenMP with tasks. I'm sorry for this thing. It should have. Let's see if I can. Okay. Now it's gone. Okay, let's see. Here's a stupid, naive implementation of calculating the Fibonacci number sequence. I think you have all seen it. You recursively call yourself, and so each Fibonacci number is the sum of the two previous ones. So you just, if you want to calculate Fibonacci number 42, you begin with calculating for 41, and then for 40, and then adding them up. It's stupid because it calculates the same thing over and over again, but it's a good didactic example here. So there's parallelism here, there's task parallelism here, because these two calls can be executed in parallel, right? And there is a need for communication, because when you cannot return from the call here until you have calculated both A and B. So there is a need for synchronization here. So with OpenMP, this is pretty easy to express. You specify that each of these fib calls are tasks, Fragmented task, that encapsulated this call into its own sort of schedulable unit, and there's a runtime scheduler that manages it. You have to specify that A has to be shared, because the thread that executes the return statement, well, now these tasks may be executed on the same thread or on another thread. We have decoupled the parallel activities with the threads. So these tasks can be executed on any unit. So in order to be able to communicate with the thread that executes the return, you have to do two things. You have to specify that A and B are shared, otherwise they become private variables to the task. And you need to specify that you have to wait here until these two tasks have been done. There is some stuff to be done to kick it off to begin with. You have to do it, make sure it's parallel, and then single thread will start the whole execution, but otherwise it works nicely. So what happens here is that when you create a parallel region here, you create a number of threads. They will execute, and when you come to a halting point, like the Fragmented single, there's one thread that will execute the fib call. The other threads, they will just wait for work to be done. And then they go about and do some work. And I have a picture here, yeah, that's actually the next. The tasks are put on queues with work. So of course they execute their own tasks. If you create a new task, they are put in a queue here, but only when one core becomes out of work, it will then attempt to steal from someone else to reduce the load of the other guy's work and to have something else to do on. Actually, you steal not only one task, you steal a bunch of tasks, typically, which are on a load. Because the idea here is that you create a multitude of tasks. You have many tasks, and when so that you have as often as possible, you don't need to go and steal from others. You work on your own. And with, for instance, this Fibonacci sequence. If you look at the tree of tasks that gets generated, there is tremendous amount of tasks, and so there's a lot of tasks. Parallelism is quite good on 4 threads, for instance, and not much communication between the different threads. The time is basically up. I wanted to show you some code and some runtime, but there is something wrong with my computer. Some questions. We can stop now. Yeah?
So with the new C++ 17 and parallel algorithms, are there things that TBB can provide that is not provided?
Oh yeah. Oh yes. Yes. So TBB works with task parallelism inside. So even a for loop is worked as a task parallelism. So every TBB algorithm works seamlessly with other TBB algorithms. In fact, I think Intel has now also merged the runtime system of their OpenMP implementation with TBB, so TBB works very well with their own implementation of OpenMP. You don't need to get an Intel compiler to use it. Clang uses the Intel runtime system for OpenMP, and then you have this open source implementation of TBB. There are other patterns also that are supported in TBB that you cannot do with the parallel algorithms. For instance, pipeline pattern. You can build pipelines with parallel code, so one pipeline stage is executed in parallel with the other pipeline stages, and many more. You can do a lot of reductions and stuff like that. So it's complementary. Intel has its own implementation of the standard template library, which works well together with TBB, and Intel has long been the forefront of implementing stuff for parallelism. They have really good software in this area. Something else? Yeah.
Yes, as a potential application that we can benefit from that, you mentioned some only basic teaching examples.
Yeah.
For example, I'm working with, I do image processing.
Yes.
So I do a lot of filtering, like image transformations or convolutions with filters, which I think it's vectorized. I don't know if I can somehow benefit from this. Do you have any suggestion?
It depends. I mean, many image libraries. I suspect that you use libraries that not write the code too much yourself, and the libraries, are sort of OpenCV and stuff like that. They are parallelized. You can typically choose. They are usually using both vectorization and OpenMP and TBB are quite common in these libraries, and sometimes you can choose which one to use. So it might benefit you to know a little bit about the different models and trade-offs, so that you not always use the default. But I would say that try to look into the Intel technologies, because they work better together. So if you have a library that works with TBB, for instance, then you can utilize TBB yourself using the library, and they will work nicely together. But also OpenMP, if you have something, then you don't need to go to Intel. If you have an OpenMP library parallelized with OpenMP and vectorization, then you can write OpenMP code, and with tasks, I should emphasis, and that would work better. So one of the really good benefits of tasks is that you can compose stuff. You don't. The threads are no longer, since the threads are sort of a proxies for processors. If you have a library with threads and then you write your own threads, you have more threads than cores, and they have to schedule and so on. They don't work well together. But if you have a library that works like TBB, that creates tasks, and then you have your own code where you create tasks with TBB calls, and then these tasks are scheduled with the same scheduler, and they work nicely together.
Yeah, in fact, you mentioned OpenCV. From the very beginning, like 12 years ago, they had the flag to compile you with TBB.
Yeah.
And I think it's because Intel was supporting OpenCV until they embodied. So I think they were working together, TBB. But recently, like 2 or 3 years ago, I think they also have an OpenMP platform.
Yeah, that's what I've seen. They have both.
So I'm a bit confused. I don't know. Maybe you can.
So I don't know.
Suggest that it might be better with the task scheduling. So this leads to TBB, or.
Yeah, that's my. I think that's usually better. That if you want to write parallel code yourself, that work together with the OpenCV code, TBB I think is the way to go. Yeah.
Can these libraries like either OpenMP or TBB can you use those tasks for several of them parallelly, or it's only like can you, for example, distribute TBB tasks amongst multiple servers?
No, this is shared memory only. Yeah. So there's a scheduler that schedules on the threads in one operating system instance. I can just say a few words more what's sort of happening with task parallelism. I should mention that there are many task parallel models. So in C++, you have OpenMP, C++, TBB. If you run on an Apple machine, you have Grand Central Dispatch, which is Apple's implementation of this. If you run C#, .NET, you have Microsoft TPL, the task parallel library. In Java, you have the fork join library. If you write Erlang, you have processes. They also scheduled with the work stealing scheduler. X10, which is a Java extension, if you like. You have activities and so on. So the concept exists in quite a few systems. What's also coming is that you can use tasks to implement heterogeneous processing. So ARM has a processor called the Big Little processor. If you I don't know if you heard about it. It's a cluster of processors where some are small and very power efficient, not very performant, and some high performance and power hungry. With a task parallel library, it doesn't really matter that these are the different performance. You can schedule the tasks quite efficiently across these. But real heterogeneity is challenging. And here is an example where we used what happened now? Time up? Okay. We with OpenMP version 4 had the possibility of adding, let's see, dependencies to tasks. You can specify what data a task depends on, and then the runtime system will schedule this task only when this data is available. So it becomes a data flow model, basically. So you can write very nice data flow models using OpenMP tasks. This exists also in TBB, this kind of possibility. And what we did in the research project is that we defined a system, runtime system that could package these tasks onto 3 different kinds of architectures. You have a normal CPU, which is a multi-core. We had a GPU, which ran CUDA code. And then we had a Tile Pro 64, which is a 64-core embedded architecture. And the same code could run on, well, we had to write a little bit. For the Tile Pro 64, it was the same. We just needed to specify that this was running on Tilera. For the CUDA, of course, we had to write this CUDA kernel. that was different. But then the runtime system could then in runtime choose which one of these machines or 3 different kind of processors should you run your code on. And even if they don't share memory, and this goes back to your question about servers, it's possible. I mean, there is no system that implements it, but it's possible when you have the dependencies and you specify all the dependencies, then you can package the task code together with the data and ship it to where it's going to be executed. And as long as the amount of work is big enough so it sort of amortizes the cost to move it, it's perfectly doable. And this is something that people are working on now, and in OpenMP actually there is an offloading model where you can offload certain for loops to GPUs, so that works that way. Okay. Yeah, that's about it. Thanks for your attention.
Okay, everyone, so the pizzas are in rotation. You can go.
Thanks.
So I'm gonna reboot my machine and then we bring it to the pizza room and then we can have a look at some code if you like.